Hello. So we're going to talk about infinite matrices today. Infinite matrices and spectral theory. So we'll try to look at what happens linear algebra in infinite dimensions and do a bit of eigenvalue theory for that beast, the linear maps there. This is called spectral theory. So it's going to be a bit hard and a bit introduction to research somehow. These are things which are really complicated in infinite dimensions. So let's have this presentation found first. Here we go, infinite matrices and spectral theory. So in order to get started, we have to be a bit abstract. So let's go back to linear algebra and do a few things that we avoided so far. I mean, linear spaces. These are not really finite dimensions where anything is obvious. I mean, linear spaces are just Rn in the real case and Cn in the real case. There are no other ones. But in order to deal with infinite dimensions, it's better to do it this way a bit abstractly. So what's a linear space or complex space, vector space? There will be all complex the spaces here. So it's a space with the sum and multiplication by scalars. And the rules are those that you see here, 1, 2, 3, 4, 5. It's exactly as for the vectors, all the trivial things that happen there for vectors. We'll put them as axioms here. So the thing is now, are there any other axioms to be added? And the answer is no. I mean, there are so many things which are trivial that can be said about vectors. The idea is that they all reduce to these 5 things. Out of these 5 conditions over here, you can deduce anything trivial somehow that can be said about vectors. What are the examples? Cn, of course, c to the infinity. I mean, you can take also infinite sequences and all this will work, of course. The usual matrices too. I mean, you see you have sum and multiplication by scalars, so all this will work too. And also many spaces of functions, which are infinite dimensional, like the continuous functions on 0, 1, right? This is something that you know, sum of continuous is continuous, multiplied by a scalar stays continuous, and all these formulas are just clear. Now, what can we do with these linear spaces? We're interested in linear maps between them, right? We don't have matrices there, so we have to do it this way, linear maps first. So linear map is called linear when the sum goes to the sum, multiplication by scalars go to multiplication by scalars. Now, at this level of generality, we can do much. So, but here is, however, an interesting theorem. So if you take a linear map, first of all, the kernel, I mean, the things which are mapped to 0, it's a linear space. I mean, if you take a sum, things which are mapped to 0, it's mapped to 0 too, and also we can multiply by a scalar, so this is clear. Also, the image is a linear space. I mean, if you take f of x, f of y in the image, f of x plus y is their sum, so it's also in the image. Same for the scalars. So these are trivial things. Now, the non-trivial thing is that the dimension of Kerr plus the dimension of the image is the dimension of the space here, V. So is this true? I mean, well, if one of them is infinite, of course, V has to be infinite. So it's trivial, the equality, infinite plus something equals infinity. Now, in the finite dimensional case, well, the idea is not somehow, so you have your space here, V, right? And you have the kernel, which goes to 0, and the rest somehow, the rest goes to the image in a bijective way. So you have a kind of decomposition here, kernel. And this is not exactly the image, it's somehow the pre-image. And well, if you have this kind of decomposition, I mean, dimension of this plus dimension of this, dimension of everything. Well, in practice, it's a bit technical. You have to take a basis in Kerr and complete the basis in MF if you count. That's the correct count. I mean, it's just obvious from this picture. Now, well, we're mostly interested in infinite dimensions because in finite dimension, everything is trivial. So the idea is that any vector space, finite dimensional, has a basis, which means U1, En, some vectors there, such that any vector can be written as a combination of them. Now, once you have this V Cn, I mean, what's a vector V in your space? You must have a number V1, a complex number, another one V2, and another one Vn. So you need then complex numbers and coordinates with respect to this basis. So it's exactly as Cn. I mean, having a vector v is the same thing as having a column vector in Cn. So v is Cn. So as a consequence, the linear maps between finite dimensional spaces, just linear maps between powers of Cn, so they are matrices, okay? So game over. Now, as I told you, we're mostly interested in the infinite dimensional case. And here, in order to get results, we have to put some more structure, these scalar products. These are very important because on Cn you have the usual scalar product, right? Sum of xi, yi bar, that's your scalar product. And this is there. I mean, you can, it appears somehow behind many computations with matrices. So we have to assume that these things exist in general in order to get results. So the definition for it's an operation which is linear in x until linear in y. That's the convention. You have this axiom here, and it must be positive, strictly positive for x non-zero. Now you have such a beast. If you set, this is called the norm of x, square root of this positive quantity, then first you have the Cauchy-Schwarz inequality, which can be proved, well, just look at this thing, norm of dx plus y to the square. If you expand, that's a degree 2 polynomial in T. As this is positive, the discriminant must be negative. The discriminant is, I think, 4 times this minus this. So it must be an inequality. Now, out of this, you get right away, this is called Minkowski inequality. Norm of x plus y is more than norm of x plus norm of y. And this shows you exactly that if you take x minus y, that's a distance. I mean, it satisfies the triangle inequality. So very good. Once we have a scalar product, we can talk about distances. So we can talk now about Hilbert spaces. So these are the vector spaces, complex, with a scalar product, such that the space is complete with respect to this distance. Complete meaning that Cauchy sequences converge. So what are the examples? Of course, Cn, L2 of n, if you want, you can also take infinite sequences. Also importantly, we can take spaces of functions. I mean, the scalar product is the integral of fg bar. Actually, this third example generalizes the first ones, because if you take x to be a discrete space like 1n with a counting measure, you get Cn, right? And if you take volume, you can take an infinity space as well as a counting measure. You get the second example, so that's the most general example somehow. Now, what can be done with these Hilbert spaces? And the first thing is that you can construct a basis, an orthonormal basis. Why? Because you start on an arbitrary basis, which is not an orthonormal one, and then you can do Gram-Schmidt. I mean, orthogonalize the thing. Okay. Now, once you have a basis, it's just for linear spaces. It becomes something trivial. I mean, any vector in your Hilbert space, you just need a sequence there of coordinates, right? The sequence is no longer finite. Of course, it's indexed by this I, the number of elements in your basis. So to be more precise, H is L2 of Y. L2 and not all the sequences, because things have to converge. I mean, the norm of the vector must be finite, right? So this means that the sequence there in L over I, this is in I, must be square summable. So all this looks, when you first see this, you'll say, so why bothering with all these abstractions and arbitrary Hilbert spaces? You just take L2 of I, right? Because they're all equal to some L2 of I. This is wrong, because for spaces of functions, which are very important, if you try to do this Gram-Schmidt and everything, it's going to be very hard, okay? It's so-called orthogonal polynomial, things like that. So this is something theoretical. Of course, it's a bit of a mystery. Magic's happening here. In practice, it's better to think of Hilbert spaces somehow as things on their own. Now, well, but this point of view is very useful, because it tells us that if you look at linear map between H and H, these are somehow infinite matrices, or maybe finite if H is finite dimensional. So to be more precise, let's take a space of the basis, then L of H, so the linear maps from H to H, embed into the infinite matrices, the index I. I is the indexing set for the basis. And the formula is the usual one. I mean, the matrix coefficients are Ti, J, scalar Y. Okay, when H is finite dimensional, this is bijective, so we get the usual matrices. So what we'll be doing in what follows is really infinite matrices. With the remark, however, that I was telling you for spaces of functions, things like that is better not to use a basis because the basis is not explicit. So this remains something a bit theoretical. Now, in order to do really theory, we need to assume that our operators, I mean, our linear maps within H and H are bounded. That's something important. So it's automatic in finite dimensions. In infinite dimensions, if you don't assume that, you won't get results. So here's the theorem that you need. So take the operators which are bounded in the sense that this quantity here, I mean, the norm. Take the unit ball, and then you see the point there where, well, you see how it inflates, and take the maximum norm which appears there, because the norm of the operator must be bounded. This is not automatic in general. So what can we say about these guys? So they form a complex algebra called B of H. Well, this is clear. This is complete with respect to the norm. Why? Because if you take a Cauchy sequence, you can define point-wide limits, and that's your limits. Then also you have an involution, somehow a kind of adjoint matrix given by this formula, exactly as for adjoint matrices. And in this setting, this comes from the fact that this guy here is linear in X. So it should be X scalar product with something. And finally, the norm and involution must be related by this formula over here. T star is t to the square. And this is something that, this is clear for matrices. I mean, on both sides you have the square of the biggest eigenvalue, absolute value. In general here, this can be proved, let's say, by double inequality, no problem. Now with this, we can do some spectral theory. So talk about kind of eigenvalues. So do it in a general setting of the C-star algebras. So C-star algebra is exactly something like B of H. So you take an algebra with a norm, an involution, and share related by this formula. So basically, it's B of H, and it's a algebra satisfy this. We'll see later where we're working in the setting. So with this, we can talk about the spectrum of elements. These are the lambdas such that A minus lambda is not invertible. Of course, well, for matrices, you get the eigenvalues. So as first result now, A, B, and BA have A, B, and BA have the same spectrum, but outside of zero. So why? Because Y minus AB is invertible. If you know if 1 minus BA is invertible, by linearity we can multiply by a lambda different from zero. At zero is not true because if you take the shift on them to of n, it's adjoint to this and this. It's the identity. Otherwise, it's not the identity. You have the problem there at zero. Now, what can we do next as basic stuff? So we have the following formula. Spectrum of function of A is function of spectrum of A for any rational function. Having its pole outside the spectrum because, well, if you want to apply F is a fraction, right? If you want to apply it to A, but something there on the bottom must be invertible. So this means that the zeros there must be outside the spectrum. So is this true in the polynomial case? Well, just factorize your polynomial. So all these guys must be invertible. You're done. In general, where you have a fraction, use this trick. I mean, pick your lambda and take this polynomial, apply this, and you're done. Very good. Now, an important result is that in a C-star algebra, spectrum of normal elements is on any disk, of unitaries is on any circle, self-adjoint is real, and of normals. For the normals, the spectral radius and the smallest radius of the disk containing the spectrum is the norm. Why is this true? So these are things for matrices. We haven't proved this already, so that's the proof. It works in a C-star algebra. So the fact that, what was the first thing? Norm 1 is ending disk. Well, we just need the inversion formula, that's it. Now, spectrum of unitaries is on any circle. Use this thing with rational functions for 1 over z, which is rational. So do this, you see, here in the middle, I use the fact that A is unitary, minus 1 is A star. So finally, the spectrum is lambda such that lambda minus 1 is lambda bar. So this is the mid circle. Now, once you have this, you can prove that the spectrum of self-adjoints is on the real line because you see this function here. This is something quite tricky. Maps the circle the real line. So you can always pass somehow if you apply this function to complex numbers you get from here to here, and from operators you get from unitaries to self-adjoints. Get this? And finally, from the spectral radius, you want to prove that the spectral radius is the norm. So you do a Cauchy integration like this. Apply the norm taken root, so you get one inequality. And in the other sense, the idea is that you're done if here you have norm of A. And well, in the self-adjoint case, you're done because this is, you use norm of A square is norm of A square. Remember, in sister algebras, you see this condition satisfied. In the self-adjoint case, you're done, and in general, you use once again this, and in the normal case, you get the result. Now, at the more advanced level, so this was good. I mean, we have a bit of eigenvalue theory for the operators on a Hilbert space and more generally sister algebras. Now, with sister algebras, you can do a lot of interesting things. So the idea is that given a compact space X, the algebra of functions continuous on X is a sister algebra, right? To put this norm, this involution just works, the sup norm, the evolution. And on the converse, which is due to Gelfand, it's a very big result that any commutative algebra is of the form C of X. The spectrum being, so let's think a bit, we want to recover X from C of X. That is that to take the characters, I mean the maps which are linear and multiplicative from A to C. And these guys here, well, it's a compact space with this topology. I mean, evaluation maps must be continuous. Now I have to prove that it's involutive, isometric, and surjective, and this follows from the spectral theory we're doing, and with some Stone-Weierstrass at the end for surjectivity. A very, very nice result. And this has two applications. So first application is more or less the spectral theorem. So if you take a normal element, like for instance, if your algebra is all the operators B of H, you take a normal operator there. But in general, you take a normal operator in a sister algebra, then the algebra that it generates is commutative. So by this Gelfand theorem, it should be C of something. And that something is a spectrum, and well, it can only be spectrum of A. So spectrum of A. So you see the functions of this A guy are actually continuous functions of it. So you can extend this functional calculus formula instead of rational, how it works with continuous things. And this is very nice, more or less the spectral theorem. So we've done that. Now, there's another application which is interesting too. So once again, Gelfand was telling us that any commutative sister algebra is functions of a compact space. Now, in general, you can say that given an arbitrary sister algebra, this is somehow functions on a non-commutative space. But that's non-commutative geometry. So this is very interesting, and it's a bit of an introduction. So what we learned today, so first we completed a few things that we haven't seen already for matrices, like the spectral, unitaries, all that, and then the spectral theorem. And with this, with sister algebras, you can do a lot of things like non-commutative spaces, geometry, hermetic, quantum mechanics from this point of view. So I hope that you like it, and I see you soon for the last lecture. There we'll go back to finite dimensions and do a lot of matrix tricks. See you.